right, welcome to lecture 2. So we're going to be having a brief math review on trigonometry. We're going to talk about units. We're also going to do a little bit on SI or on significant figures, and then we are going to be getting into vectors. So there are going to be 3 videos for today's lecture. Again, we didn't really cover anything physics related last time, so I'm not going to have a last time slide, but starting on our lecture on Monday, we will be having those. So today we're going to be going over a brief trig review. Some of what we're going to be talking about with trig, we're not going to do examples until we get into our vector section. We're going to be talking about units, and we're going to be talking about significant figures as well. Those are in chapter 1, section 8. Video 2 is going to be vectors and coordinate systems. So the way that this today's slide is going to work is I'll have the chapter and section in parentheses so you know what to look at later. And then in the third video, we're going to look at vectors and components. So with trigonometry, we are going to be focusing on using right triangles and right triangles only. So this is going to, cut out a lot of weird stuff related to triangles and other shapes. We're just focusing on right triangles and on right triangles only. So here we have a right triangle. Here we have the hypotenuse labeled as H, and we have 2 sides labeled A and B. So we have Pythagorean's theorem for that, which says that a squared plus b squared is equal to h squared. Now at least when I learned this original triangle, h was c, but because we're going to be dealing only with right triangles, we're just going to refer to it as the hypotenuse. So with Pythagorean's theorem, we're going to be using this a little bit later in the semester to help recombine our triangles back into a hypotenuse value. And with some of what this trig review is doing is just kind of refreshing your mind on the fact it exists. We will be covering it again, like I said, later in today's lecture. And then when it comes to when we're using some of this stuff, we'll talk about it again the first time, maybe the second time, but after that we won't. So with Pythagorean's theorem, maybe in some situations we'll have A and B, and then we'll need to go through and find H. Now the trigonomic ratios are the things that we are going to be using rather frequently in order to take a triangle and split it into components. So again, that's something we're going to be discussing with the vectors. But here we have, again, our hypotenuse labeled, and here we have an angle that has been chosen for us. It's this left part of the triangle. Now when we are now labeling our triangle, it's going to be relative to this particular angle. So the side that is not connected to the triangle is referred to as the opposite, and we have the hypotenuse and the other side. The other side here is referred to as the adjacent. Now it is completely valid to instead say that I want my angle to be the other one, right? So we have a right triangle, so one of them is 90. One of them is the left part of the triangle here, and then we could have the top one. And what that would do is it would take us to relabel our triangle such that we have the adjacent where the opposite was for our other angle. So it's just making sure when we draw out our triangles, we need to make sure where our angle is identified from, because that's going to determine which part of the triangle is opposite and which part is adjacent. The hypotenuse doesn't care where the angle is, it's just the hypotenuse value. It is always the longest side of the triangle. Now it's important to note which angle we're working with, because that's going to help us determine sine, cosine, and tangent, which one we are using with which sides. And a way to remember sine, cosine, and tangent and what goes with them is something referred to as SOHCAHTOA. Now I'm going to be 100% honest. I learned this in my trig class, and it didn't make sense to me till I was in Calculus 2, taking calculus with the head of the math department at UC Merced. And I was so fascinated with the fact that this is what SOHCAHTOA represented. I audibly awed to the point where the professor turned around and asked me if everything was okay. So I understand if this doesn't help you in any way, shape, or form, because it sure didn't help me. However, I know it helps some people, so I want to spend time going over it as SOHCAHTOA, but it represents the same things that we see in the trigonomic ratios on the right over here. So what SO tells us is that sine is equal to opposite over hypotenuse. So when we look at the trigonomic ratio, we have sine of our angle is going to be equal to the value for the opposite side of the triangle divided by the value of the hypotenuse. So if we're using the original angle we were defined as, so this left angle over here, we would take the value of the opposite side and divide it by the hypotenuse. We then can look to the middle part, the ka. Ka is going to be representative of cosine. So cosine is equal to adjacent over hypotenuse. So now we are using the adjacent portion of the triangle in conjunction with the hypotenuse. So it's important, if you are using the same angle for calculations, you cannot have sine and cosine of the same angle to represent different aspects. So let's say hypothetically we were using the definition of sine to help us find the value for the opposite length. So what we can do is we can just multiply both sides by the hypotenuse. And we end up with something like this. So we'd have opposite is equal to hypotenuse divided or multiplied by sine. I cannot then say that the adjacent is equal to hypotenuse multiplied by sine. This does not work. Because we are using the same angle, we cannot have sine and cosine working to identify a different side of the triangle. Or sorry, we can't have sine and sine being used to identify different parts of the triangle. We would have to use adjacent is equal to hypotenuse cosine theta. Because here, we are assuming that we are using the same angle. So these two are the same angle, which results in us not being able to use sine both times. So this is kind of how you're going to use that. I know some people only like using sine, so they'll change which angle they're using. That is a personal preference. I'm never going to be doing examples that way, but I know some people prefer it. I'm going to tell you this a couple of times through the semester. You are an adult. You can make your own decisions. This is one of them. Now, if we go back to our SOHCAHTOA, now we need to do TOA. So TOA is tangent, and it's equal to opposite over adjacent. So here we're not using the hypotenuse value at all in order to identify information associated with our angle. Now, later today, what we're going to be focusing on is using sine and cosine. A little bit later in the semester, we'll talk about using tangent in more detail there. Now, all of you should be either in Calculus 1 or you're probably in a higher level calculus class at this time. Calculus uses radians. So your calculator might be in radians. In this class, especially when we're dealing with trig, we are going to be using degrees in a very large majority of the time. So please make sure your calculator is set to degrees. Now, some of you might be using your phone as your calculator for doing some quick math and stuff. Calculators tend to be set in radians, if I recall correctly, so just Make sure that your calculator is set in degrees for that if you plan on using it to kind of work along with the lectures. So we're going to come back to using sine and cosine in the next two videos. So I don't want to spend too much time harping on how exactly they're going to be used. We'll come back to that a little bit later today. The next thing I want to talk about are units. In particular, we're going to be using SI units, so the International System of Units, or sometimes it's just referred to as metric. So this table here shows us the basic units for SI units. We can then take these and combine them into more complicated units, but they can all be broken down into these here. Now we're not going to be, at least at the beginning of the semester here, we're not going to be worried about these bottom ones. We're going to be focusing on length, which is measured in meters. Well, let's ignore these qualities. So the symbol for meter, actually no, let's keep that, is M. And very frequently when you're seeing it in equations, you'll see it as L, maybe you'll see it as X, Y, Z, or R. So these are the variables you would see. When it comes to talking about a distance, in physics, we're typically going to be referring to it as a distance in meters if we want to be in SI units. So you are, I don't know how many meters tall. Let's say you're around 6 feet tall, so you're about 2 meters tall. Yes, it is possible to have longer distances than a meter. In fact, we very frequently measure things in kilometers or in things smaller than a meter, like centimeters or millimeters. So for that, we need some other way to represent our values because we don't always just want to have everything in terms of meters. So for that, we have common prefixes. So here in the common prefixes, on the left side of the column here, we have how it's pronounced. Here we have the power of 10. So for example, if we look at kilo, it's 10 to the 3. So 1 times 10 to the 3, in terms of, let's do this for the mass SI unit, which is kilograms, 1 times 10 to the 3 grams is equal to 1 kilogram. We could do the same thing with meters. And so basically what we're doing is saying we don't want to have to write out all these decimal points. I don't want to have to write out 1,000. I don't want to, if I have 9 to the power of 9, I have something to the giga. I don't want to write out 9 numbers. Something, physics is commonly thought of as being hard, when in reality, almost every physicist I've ever met in my life has been extremely lazy when it comes to writing stuff out. Concepts, they're like, yeah, these concepts are great, but they then kind of shoot off to engineering and they're like, go figure something out with it. Like, what do you do with it? Go figure that out. And they give it to engineering. So physics likes coming up with ideas, but in a lot of extents, pretty lazy. So that's why we use these prefixes instead. So with units, we are going to be seeing these pop up starting on Monday. We'll be using them really, really roughly today, where it's just going to be like, hey, these are the units. But with these prefixes, you are going to be expected to memorize what they represent. We are going to, very common in this class is we're going to be focusing between kilo and micro. So this is going to be where we are for a majority of this particular class. And as you move forward in the physics sequence, the prefixes that you use are going to end up growing. So as we start introducing units, I will kind of go over these again, but kind of start maybe committing to memory the relationship between kilo, centi, milli, and their power value. So something else we're going to be doing with units is converting them. So here's some, it says it's a useful unit conversions, but a majority of the textbook is given in SI units, so we don't really need to worry about it. But I want to show you a method of undergoing unit conversion. And the reason I'm going to show you this now is later in the semester, unit analysis, so making sure your units match up at the end when you do some math, is going to help you make sure that you've done something correctly in terms of doing your math and your algebra. So let's go ahead and do this. So I'm going to want to take my height, which is roughly 5 feet, 5.5 inches. So this is my height, and I'm going to want to convert this to meters. Well, I have in my useful unit conversions, I have inches to centimeters. I don't know how many fractions of a mile tall I am, so that's not useful. I'm not a mile per hour, I'm not some unit of speed, so that's going to get rid of that one in meters per second. If I knew my height in meters or kilometers, I wouldn't need to go through this, so I need to use this top conversion here. So the first thing I'm going to do is make sure that all of my values are in inches. So I have 5 feet. I need to multiply this by 12. So the way we can do this is 1 foot is 12 inches. And so what's going to happen with this type of formatting is the feet are going to cancel out, and my resulting answer is going to just be in inches. So 5 times 12 is 60. I then need to add my 5.5. This is all in inches, so I'm roughly 65.5 inches. So now that I have my inches value, I'm going to go through and convert it to centimeters. So I'm going to have 65.5 inches. Another way that sometimes this format is written out is just using fractions. So 1 inch is 2.54 centimeters. But I don't want to stop at centimeters, right? I want to go to meters. So a centimeter, there are 100 centimeters in a meter. So I'm going to divide by 100 centimeters, and that's going to give me my value in meters. So I'm going to take my 65.5 inches, I'm going to multiply it by 2.54. And that's, if I just look at this part here, I got 166.37. So that would be my height in centimeters. Because if I, again, look at my units in the numerator and denominator, they're going to end up canceling out, and I have centimeters. Now, I need to go through and divide that by 100 in order to get my answer in meters. So when I plug that into a calculator, I get 1.6637 meters. So by being roughly 5'5.5", I'm about 1.6637 meters tall. So this is one method in which you can go through and do unit conversions. Towards the beginning of the semester, I'm going to try to make sure I always show my units and show my units canceling out. So here, having the meters cancel out, for example. That way you can see how I go from my initial unit, or in this case, units, to the final unit. So I'm going to kind of go through the steps of writing this out. As the semester goes on and we get more familiar with unit conversion, I'm going to stop doing it in such a rigorous form. The last thing I want to talk about is, for this video, is significant figures or significant digits. So some textbooks use significant digits, some online sources use significant digits, while others use figures. I very commonly abbreviate it to sigfigs. It's the same thing. It's, again, lazy, don't want to write everything out. So the goal of significant figures is to accurately describe your answer. Now, there are different levels of accuracy out there. And the goal of significant figures is to make it so that it's correctly describing what's happening. So for example, if you include too few figures, your answer becomes inaccurate. So you have an age. You are a certain age, old, whatever that is. I happen to be 31. So if I used too few significant digits, let's say I only want to use one, I could say I'm 30. That's not that big of a lie. But what if I want to round to the nearest 100? I would be 0. I'm definitely older than a newborn baby. That doesn't make any sense that I would want to round to 0 for my age, because it's not accurate for what I'm able to do. Whereas if I rounded to 30, I'm in my early 30s, that's close enough. Now I could do the exact opposite, where I can have too many figures. So let's say I wanted to tell you my age, but I gave it to you in the exact number of seconds old I was. It's measurable. It means something. It's accurate. It tells you exactly how old I am. But it can be measured. It's just not helpful. It's not helpful if I tell you how many seconds old I am. You'll just be like, wow, that's really annoying. So the goal of significant figures is to accurately describe your value. And so with that, I think this schematic here from the textbook does a pretty good job explaining it. So here we have a number. Sorry, we have 0.00620. Now, I can put as many zeros in front of this as I want. And because I can add as many as I want and it doesn't change the value, they're insignificant. They do not matter, and they shouldn't count for what my answer is going to be. 6 and 2 here are going to be significant because they're actual numbers describing something of relevance. This 0 here is going to be something interesting. So for chemistry, from my recollection of it, that 0 always counts. In physics, the 0 doesn't always count. The way you are going to treat 0 at the end of a number in this class is by looking for a key word. If you see approximate or approximately or something like that, the last 0 does not count. If you see something that says, in the text down here, it says reliably known or accurate, or accurately or anything like that, the 0 or last 0 does count. Now, I know this is a really big nuance, and it's annoying. I'm going to be honest, it is annoying that there's not a consistent rule on the 0. In this textbook, if it gives you a value with a 0, treat it as exact or accurate or reliably known. So in this situation, it gives us 600,620. Here we're going to say that the 0 is significant and we would need to count it. So that would mean that this particular number has 3 significant figures. And if we shifted this decimal point, in this case 3 places to the right, we could write our number out instead as 6.2 times 10 to the negative 3. So this here is how you could, ensure that you had the correct number of significant figures. And again, as we start getting into more math, so in the next couple of videos, I'll talk about this again and kind of how we know what's going to be important. But I just want to give you a couple of quick tips about that. So you're going to be doing math in this class. Typically, when you are doing math, you should carry 2 to 3 extra digits the entirety of the time. So if you're doing everything in your calculator and you're able to store numbers and things like that, you're going to be using 10 digits. That's always going to be more than you need. That's okay. But 2 or 3 extra ones are going to be beneficial because it's going to help you prevent rounding errors. So when you're giving your answer, the number of significant figures in your answer should match the lowest number of significant digits or figures given in the question. This textbook typically has 2. So most of your answers should have 2 significant digits. Some questions will have 3, but the numbers in the question tells you how many numbers your answer should have at the end. That is the formal way in which that should be done. Where constants don't change the numbers, it's just whatever is given in that question is what's determining it. Now, I'm okay if we don't follow this exactly. And if you want to give me a maximum of 2 extra significant digits or figures, whatever you want to call them, I'm okay with that. I'm okay if you're not perfect with sig figs, especially at the beginning. It's a learning process. So I'm okay if you give me some extra ones. However, I do not want all 10 numbers that your calculator displays. That is too much. I want you to put a little bit of effort into figuring out where should I cut off my number and make sure that I've rounded it correctly. So we're going to get a little bit of practice with this in the next 2 videos as we do some examples. But again, with everything that I've talked about in this video, as we start introducing the different ideas in this class, I'll cover them again the first time a little bit on the slower side, and then as we keep seeing those things, either I'll gloss over it or we'll cover it a lot faster. All right, so that's going to wrap it up for the first video. Make sure to watch the next 2 videos as well.